Cox survival regression procedures. Cox regression uses independent variables to predict time to event outcomes, statistics which cannot be accurately estimated by linear regression or logistic regression because they cannot treat censored, non-event data. So in this instance, we will estimate what causes wars to end and other wars to continue. And Cox regression allows us to examine the different time periods. Now the data we're going to use is a data set by Dunnigan and Martel from a Rand Corporation study in 1987 with 355 cases. It's called the Dunnigan and No-Fee data. So we're going to go open up the data set. So Dunnigan No-Fee war data set. So here are the values. So the model I originally want to look at is to determine what causes wars to end at 2,000 days as compared with those wars that continue. And I want to do this by looking at the victors' population divided by that of the defeated, demographic preponderance, the victors' military manpower divided by that of the defeated, military preponderance, and the victors' losses divided by those of the defeated, loss preponderance. I actually ran those three independent variables in multiple different models, and loss prep is the only variable that is ever significant or nearly significant. Now this model, the Cox regression, is based on Meyer-Kaplan models, and these actually date back to the First World War, when the earliest statistical techniques were applied in the triaging of patients, because medical resources, particularly near the front, were scarce. And so unfortunately the decision was made to come up with a math to choose which patients were most likely to survive given a certain availability of application of medical supplies. So that's where this comes from. And we've since applied it to any event which terminates, like a treaty or a life or a war. So it is possible that different variables matter depending on the already elapsed time since the war began. The dependent variable in this model is time. It's always time. And the variable that we're going to input into that dependent variable is conflict in days, which is indicated by duration or DUR. The indicator that records if the event has occurred or not, such as whether the war has ended or not, is entered under status. And here we enter the variable census, which indicates with a 0 that a value is censored if nothing happened, and 1, meaning uncensored, if the war ended on or before reaching the duration of 2,000 days. Now, the census variable was created in Excel using an if-then statement with the following syntax, which you can see in the notes, which is equal sign if H2 is less than or equal to 2,000, then 1, and otherwise 0. Now this statement means that the values in this case, column H2, which is basically the H column that you see in the SPSS file, at that column of H you have duration, which is duration of the war in days, are examined. If the values are less than 2,000 days, then the variable census will record a census value of 1 to indicate that the war has ended or died. Otherwise, such as in the instance of the duration of the conflict being greater than 2,000 days, the value of 0 will be recorded, that there were no changes and that the war was ongoing. Now, an if-then census variable can also be created in SPSS using the recode into different variables function. So let's take a look at that. Okay. So we would go to transform, recode into different variable. Always choose different variable. If you choose the same variable, you're going to overwrite the same variable, and you never want to do that. You always want to keep the old variable around in case you want to redo a transformation. So here we're going to input the numerical variable, which is going to be duration. So we put in duration. And we're going to rename this variable census. Okay? and we click change, and what that's going to do is transform the old variable duration into the new variable census. I'm going to call it sensu because I've already have it in my data set. So here we duration to sensu. So now we go to old and new values. And here is where we input the old value and then we put in the new value, and we have to click add. If we don't click add, then it's not going to insert it into this box, which is actually going to do the changes. These tables are very often used to collapse values, but as I mentioned multiple times, never undermine the richness of data by reducing it. People reduce it for publications and for tables so that the stakeholders that consume statistics can understand them better. But for those that are working with statistics, never reduce the richness of data. So under the old values, we're going to input in the range a 0 through to 2000. So this indicates any war that terminated between time 0 and 2000 days into the conflict. Now the new value is going to be 1. Right? This is going to be our census value. And then we click add and see here's the change that is going to be implemented. And then we go back and we're going to click all other values are going to be 0. Right, so there's really two outcomes. Either the war ends before 2,000 days, including 2,000 days, or it ends after 2,000 days. And then we click continue. Oh, we forgot to add, of course. Very important. See, it reminded us we had to add. So else, we click continue and then OK. And what this is going to do is it's going to add to our data set at the very end a sensu variable, which is actually identical to the census variable that we've already added here. Okay, we're going to use the census variable subsequently. So let's start with the Cox regression procedure. There's a diagnostic requirement, which is traditional. It's the multicollinearity test. You would run the Pearson's R between each independent variable. If the Pearson correlation is higher than 0.75, then the two independent variables are too closely related. And I'm not going to run this because we've run it for so many different models, but it's in the notes as a standard step and as a standard test that needs to be done, and the standard solutions to a problem apply in Cox regression. So let's go now and run the Cox regression itself. So we go to Analyze, we go to Survival, we go to Cox regression. Now notice that the dependent variable is time. And here we're going to insert duration. Now, once we have duration in, we want to indicate the status. And for status means you have to insert the census variable. Okay, so it's going to choose and distinguish between those events before and including 2,000 days, and those events after 2,000 days. Now we need to define the event, and we're going to give it a value of 1. Okay, and that's the census value of 1. And now we put in the covariates. Now, my original model had a whole bunch of preponderant variables. We're going to run a simple model here, bivariate, in which loss preponderance, which is the least not significant variable as the variable here. We then go to plots, and in the plot type we're going to click on the survival plot and the hazard plot. Okay, and then we're going to click continue. Under save, we are going to include the hazard function, which is actually a Cox-Snell residual. We're going to include the partial residuals, which are also the Schoenfeld residuals. We're going to include the log minus log survival function, LML, and the DF betas, and the X times beta. So we're going to click continue. We're going to make sure that the method is enter, and then we're going to run the model. Now, You can change the value of the census for wars lasting perhaps less than 400 days, or less than 1,000 days, or less than 3,000 days, to see if the timing of the war can be determined by different variables. In this particular model, loss preponderance between victor and defeated was the most important variable compared to the others. The others were effectively insignificant, so we would have rerun the model anyway, only with loss preponderance. So let's go now and take a look at some of the tables that we have. And again, I've labeled the outputs according to the table order, but this would change in subsequent productions of SPSS. So focus instead on the names of the tests. So we have table 3, 1, 2, 3, and what table 3 is going to give us is the omnibus test of the model coefficients. It's basically the goodness of the fit of the model. So the -2 log likelihood over here is used to calculate a chi-square, which is in the next cell, which tests whether the new model with the added covariates, independent variables, explains more than the old model without the covariates. So this is your generic significance test for the entire model. Now this chi-square value of 4.847 and a degree of freedom, which is the number of independent variables, in this case one independent variable, loss prep, means there's an overall significance of 0.028. And it shows that the model is in fact significant, which means there's no false positive, which means it can be generalized from the sample to the population as a whole. And specifically, the inclusion of the independent variable makes a difference in being able to make a prediction in the outcome on the dependent variable. So let's go now to table 4, variables in the equation. Now here we have one independent variable, which is loss preponderance, and that's a B coefficient of minus 0.045 and a standard error of 0.024, which with a degree of freedom of 1, its Wald statistic creates a significance of probability 0.058. So it is just barely not significant, but it's close enough that I've salvaged this particular independent variable. Now, some definitions. A key definition in Cox regression is the hazard rate. This is the probability of an event taking place that terminates the case. In other words, terminates the war, given that the case has survived to a given point, right? And although we make a distinction at 2,000 days, we can make estimates of survival rates, hazard rates, up to 2,000 days. And you can see the step-level functions are distributed in the chart here, the survival function at mean of covariates that we're going to look at later. So you actually have blocks of unit time, and the rates change to those blocks. Now the math logic is that the positive B coefficients mean that as the independent variable increases in value, and our independent variable is loss preponderance of the victor. So as the victor suffers more losses, 2 to 1, 3 to 1, 4 to 1, it increases the hazard rate of the event, and the predicted survival duration decreases. Obviously, a winner who's suffering more and more losses is going to concede and allow the war to end. Now, a negative B coefficient means the opposite. They indicate a decreased hazard rate and the increased survival times. So in this case, wars last longer even as the victor has a greater ratio. That's sort of a counterintuitive outcome, but it could be that you have a major power chasing pirates in which the preponderance is enormous, but yet the war doesn't end. Because the preponderance is enormous, it indicates a special kind of conflict. A very complicated sort of analysis to disentangle the case. Here we have that negative ratio, B coefficient, which indicates this is the case. So the hazard rate increases at the same value as the B coefficient, in this case minus 0.045 for the loss preponderance. So the hazard rate is a minus 4.5% for each ratio increase in loss preponderance. The ratio is 1 to 1, 2 to 1 to 3 to 1. So let's go now to so the next value on the variables in the equation is the exponent B, which is valued at 0.956. This is the predicted change in hazard or war termination for a unit increase in the predictor, loss preponderance ratio. So each unit in loss preponderance ratio is, as I mentioned before, a 1-to-1 or a 2-to-1 or a 3-to-1 and so forth. The exponent B is the ratio of the hazard rates that are 1 unit apart on the predictor. So this is the different ratios of the independent variable. The math logic is that the hazard or war termination is reduced by 100% minus 100% times 0.956. This equals 4.4% for each time period in years that the war persists. So for categorical values, such as the presence or absence of nuclear weapons, it is the ratio of the difference in probabilities between the different categories. Okay, now it depends how you construct the model, but if you look at the survival function at mean of covariates, we don't have individual years represented. We actually have duration in years as the x-axis, but we have a representation in blocks. And the exponent B can be expressed as a change in the ratio of the hazard rate, not the hazard rate itself, but the ratio of the hazard rate in these different blocks. And so there it's not by unit time, but by the blocks. So that let's take this now to the chart. The first chart, this is the survival function plot, and it shows the covariate estimated cumulative survival rate, or war continuance rate. The horizontal axis shows the time to event in years, and meaning the time to the 2,000-day limit. And the vertical axis shows the probability of the war continuing from one step to the next. All right, so if you've been at war for 200 days, there's an 80% chance the war is going to continue. If you've been at war for 400 days, there's a 60% chance of the war continuing. If you've been at war for 900 days, there's a 50% chance of it increasing. If you've been at war for 1,300 days, there's a 40% chance of it increasing. And if you've been at war for 1,700 days, there's a 20% chance of it increasing. So the second chart is the hazard function at mean of covariates. And this plot shows the covariate estimated cumulative hazard rate, or war termination rate. It shows the death rate at time t, and the likelihood of war termination at that point, given that it has survived so far. The horizontal axis shows the time to event in years, and the vertical axis shows the cumulative hazard rate, which is equal to the negative logarithm of the survival probability. So here there is some complex math that needs to be manually done in order to interpret the survival rate that's then applied here as a hazard function. And again, you can see it shows the results in the form of hazard rates rather than so it's sort of time to event in years. So it's not as easily interpretable as the survival function. So these are the outputs of the Cox regression. What is complicated are the diagnostics that need to be applied in a Cox regression, and there's a number of these. So first of all, we want to seek out influential cases, and we do that by a simple scatter plot. And we're going to scatter plot df beta, and this is the df beta of loss preponderance, the independent variable, and the case number. And so we're able to basically identify the cases this way. The df beta estimates the change in the model before and after the inclusion of the covariate in question. So we know when wars end. Now we want to see if we can predict better when wars end by using loss preponderance as an independent variable. And then we can then identify and remove extreme cases. And there are, there's several extreme cases in this model, but one which becomes very apparent in the plot, in the scatter plot. So let's take a look. The procedure is to go to Graphs, Legacy Dialogues, Scatter Dot, Simple Scatter. We're going to define it and put into the y-axis the serial of the case. And we're going to put into the x-axis the DFB1 underscore 1. So DFB1 underscore 1. And we're going to see what we can see. Now here we have an extreme case. Now I actually went through some of these extreme cases and identified them. And so we have four major outliers, which is the 1793-95 Boer Bantu War, in which you had extreme loss preponderance rates that didn't seem to affect the very long duration of the conflict. You have the Pirate War, which went from 1837 to 1860. Again, here, enormous loss preponderance, a lot of ships lost. Rather, Marines probably killed in the process in England, but the war went on. You have the Netherlands, Spain versus the pirates as well, and the naval rebellion in Brazil, 1893 to 1895. There's an Iranian revolt that involved the British, the Russians, between 1905 and 1921. So these are wars of particularly extended duration and involve irregular forces that create peculiar ratios. Probably because these are protracted campaigns that are more political than simply military. Now we have a second diagnostic. It's the assumption of the non-informative censoring. The Cox Regression model assumes that the mechanisms that cause the event are not related to the probability of the event occurring. In other words, wars end for reasons different than why they started. Now this assumption is no diagnostic, but must be conceptually plausible. This is used to control for endogeneity, where the cause lies in the antecedent causes of the model outcome. Now, endogeneity is when you're wondering if arms races are going to cause a war, thinking that arms races and wars are independent. But countries buy guns and get involved in arms races in anticipation of conflict. So clearly you have an endogeneity problem there. You have a lot of endogeneity in a lot of causal models where an antecedent cause actually selects the cases that you're looking at, the pre-event cases, in this case, countries involved in arms races that are not at war. There's obviously a common prior cause, both to arms racing and to countries stumbling into conflict. Now, the third diagnostic is the assumption of proportional hazards. All right, then there's two different tests for this. We're looking here now at the first test. The hazard function for the two cohorts, the census 0 and the census 1, is determined by the covariate and must be proportional over time. It has to have a constant relative hazard. So the interpretation is, for example, naval conflicts are twice as likely to end as land wars, regardless of when they happen. This is tested by using partial residuals, called the Schoenfeld residuals, for each covariate. The partial residual is the difference between the observed and the expected value of the covariate. The plot should be randomly scattered around the 0 of the partial residuals. So let's go ahead and do the procedure for this. We would go to graphs, legacy dialogues, scatter dot, simple scatter, and in define, in the y-axis, we're going to put in the PR1 underscore 1. We insert that. This is the partial residual for loss preponderance. And then into the x-axis, we're going to insert duration. Okay, and we're going to see what we're going to see. All right, we can see the 0 here, which is a horizontal line, and we can see that the dots are more or less consistently scattered. You do have, again, the outliers here at the center around the 900-day point, but aside from those few outliers, most of the points do cluster normally around that 0 axis. Now let's take a look at a second diagnostic for the assumption of the proportional hazards. The hazard function for the two cohorts determined by the covariates must be proportional over time, have a constant relative hazard. This can also be tested by using the martingale residuals, which must be calculated as follows. So the variable of martingale is calculated in two separate if functions. If you have a 0 value for the census, in other words, the event is censored, then it's the hazard function times minus 1. If, however, you have a 1 value, which the event is uncensored, then it's 1 minus the hazard function. All right, so what's the procedure for this? Well, we're going to cut and paste census and hazard 1 into the leftmost columns in Excel. Okay, and we're going to do this because it's easier to do the calculation in Excel. Okay, so let's go do that. All right, so first we're going to look for census in the Excel file here. We're going to go down, and rather in SPSS, we go down here and we pick up census. We're going to copy that and we're going to drop it into into Excel. Now notice, I highlight Excel, the column name, but when I paste it, I go in the column and Excel automatically excludes the name. Now in the second column, I want hazard 1, HAZ1, so I'm going to go look for it. Here we go. So I'm going to click copy, go to here, paste, and there it is. Okay, so here we've got census followed by hazard 1. Now on the next right, we're going to write some code in Excel. Okay, it's going to be an if function. If this value is met, then you do this. Otherwise, you do that. Okay, that's the basic format for all these if statements. So equal sign, if, open brackets, A1. A1, of course, is the cell right here. It sort of identifies it in itself in Excel, is equal to 1. So if it's equal to 1, then, comma, then we're going to have the calculation of 1 minus B1. Okay, so we're going to use 1 minus the hazard rate, which is here. Otherwise, we're going to do B1 times minus 1, and then we're going to close the bracket. Right, so that's the logic. And we have to just copy and paste this. Okay, so we're going to copy. Here, hit enter. Boom. Good, we've calculated it. So this is for all 355 cases, and we basically have to copy this back into SPSS. So I'm going to highlight this here, copy. I'm going to go here, insert. I'm going to go here and just paste. So here we have the paste. I'm going to go change this variable here in the variable view, and I'm going to change this to Marty, because I already have a martingale in the data set. So I'm going to call this Marty. Now we're going to generate 2 plots with martingale residuals. One with the x beta, which is the sum of the products of the coefficients and the mean corrected variables for each case, and the second with the value of the covariate loss preponderance. The plot should be randomly scattered around the 0 of the partial residuals. All right, so let's go do this. The graphs: graph, legacy, dialogues, scatter, dot, simple, define. So into the y-axis, we're going to put the martingale. Okay, which is, we did Marty. We'll put Marty in. And into the x-axis, we're going to put the XBE-1 right here, which are the x betas. And we're going to see what we get. So we can see a 0 down here. This is a 0 point. And rather, we can see the x, the vertical axis here on x beta. Yeah, the x beta is the partial residuals. So this is so we're looking at the vertical axis, and you can see there's dots on both sides. So it does satisfy this requirement. So let's go and run the next scatter plot. So here we have simple scatter. Now in this instance, we're going to leave martingales in the y-axis, and we're going to put loss preponderance in the x-axis, and we're going to run it and take a look here. And you can see here for loss preponderance 0, it seems to be more or less distributed along this x-axis, not located on both sides, but they all seem to be sort of clustered, at least at start, on the 0. So it's sort of hard to interpret this graph, but it looks like there is movement along that vertical 0 loss prep axis. So the diagnostics are generally satisfied for the Cox regression.